To find the area under a curve, or the region bounded by the given function f of x, specific endpoints or vertical lines going from A to B, and the x-axis, you simply take the integral going from A to B of your given function f of x dx. Now, if a graph of your function is not given, use Desmos to get the graph and also get the x-intercepts or the boundaries or the a and the b of your integral. So let's look at the first example. Find the area in the first quadrant bounded by f of x equal to 4x minus x squared and the x-axis. Now, you don't have to solve for x here to find the x values going from 0 to 4. You can graph this on Desmos and easily find the boundaries. Now, anytime you're finding the area and it's in terms of x, then you use your starting at endpoints for x as well. So let's set up our integral. We have a equal to the integral going from 0 to 4 of 4x minus x squared dx. And just take the integral of both terms. Well, here we can just undo the power rule, and instead of subtracting 1 from the original exponent, you add 1 to it. So our first term would be 4x 1 plus 1 over 1 plus 1, or that's 4x squared over 2. And that reduces to 2x squared. And the integral of negative x squared, again, you add 1 to the original exponent, 2 plus 1, and that's what you divide your term by. So that would be negative x cubed over 3. And we're evaluating this from 0 to 4. Now, the fundamental theorem of calculus, part 2, states that you plug in your upper limit of integration first, minus your lower limit of integration. So everywhere we see an x, we'll plug in 4 first. And per the fundamental theorem of calculus, part 2, we need a minus sign in between our substitutions. And second time around, everywhere we see an x, we'll plug in 0. Well, that entire second part goes to 0. 4 squared is 16. 16 times 2 is 32. 4 cubed is 64 over 3. And to make this easier to simplify, rewrite 32 as something over 3. Or we can rewrite that as 96 over 3 minus 64 over 3. So our final area under the curve is 32 over 3 square units. Before we look at the next example, there is special integral that you need to know. The integral of 1 over x dx is equal to the natural log absolute value of x plus your constant c. That will help us with the next example. calculate the area. This is example 12 on this PDF file I found. Calculate the area bounded by y equal to, well, 1 over x technically, the x-axis, and between x equal to 1 and x equal to 4. So over here on our whiteboard, let's set up our integral. So area is equal to the integral going from 1 to 4. F of x is the same thing as y, so that's 1 over x dx. And the integral of 1 over x dx is natural log absolute value of x. And we're evaluating or finding the area of the region from 1 to 4. So all we do here is plug in 4 first in place of x. So we have natural log of 4. You must have a mandatory minus sign in between your substitutions. And then the second time around, plug in 1 for x. The natural log of 1 is 0. So our final area is natural log of 4, which is roughly 1.386 square units if you have to express your area as a decimal. Let's look at one more example. This one I'm going to make up. Find the area of the region bounded by the x-axis, y equal to x squared, going from x equal to 0 to x equal to 2. All right, so let's set it up. Our region will look something like this, approximately. We have 0 here. 2 is here. So this is just a rough sketch of our region that we're trying to find the area for. So we have our formula a equal to the integral from 0 to 2 of f of x, or just x squared, dx. And just integrate using or undoing the power rule. So when we undo the power rule, we add 1 to the original exponent. So that would be x cubed. And we divide by the new exponent, 3. And that's going from 0 to 2. Now, when we plug in, according to our fundamental theorem of calculus part 2, plug in the upper limit of integration first. So that means we plug 2 in first for x. Mandatory minus sign. And the second time around, replace x with 0. But the second part is 0 anyway. And 2 cubed is 8. So our final area is 8 over 3 square units. What if you had 2 curves and you had to find the area between them? Well, let's look at that specific property. So this is what's illustrated here to the right. If you have two curves, and here they're named F and G, but I'm not going to really label them as such. How to find the area between the two curves if they're going up and down like this, then you have the area equal to the integral from A to B, whatever your endpoints are, starting and ending, whatever the top curve is, minus the bottom curve. So this is the formula you would use if everything is in terms of x. You have to graph. If the graph is not given for you, just go to Desmos to find the graph. Whatever the top graph is, that's what you list first, minus the bottom graph. Now, if your functions are in terms of y, then this is how you set up the area. Just take the rightmost curve minus the leftmost curve, dy. Let's look at an example where we have two curves. This one right here, indicated by figure 6.5. Find the area of the region bounded by the graphs of y equal to x squared and y equal x cubed, and the vertical lines -1 and +1. Well, since everything is in terms of x, then we use our first formula here, top curve minus bottom curve, in which the top curve is, according to our graph, x squared plus 1. And our limits of integration go from -1 to 1. So here's our top curve. And the bottom curve is x cubed. Now we're ready to integrate. So the first part here would be x cubed over 3. The integral of 1 is just x. And the integral of x cubed, again, you're adding 1 to the original exponent. So that's x to the 4th over 4. And we're evaluating this from -1 to +1. Not going to show it to you here. You can see the setup here. You plug in 1 first everywhere you see an x, as illustrated here. Obligatory minus sign in between your substitutions. And then the second time around, you'll plug in -1 for each x. And then just simplify your fractions and your numbers, and you should get 8 over 3 for your area. I'm going to continue talking about finding area between two curves in a separate video.